Alright, so today, as promised, we're going to look at how to do a infinite average. So in reality, it's called the average of a function over an interval. But first let's remind ourselves how a typical average works. So let's just pretend we're trying to do the average of a bunch of temperatures. So maybe at 1 o'clock the temperature ends up being 50 degrees Fahrenheit. My apologies in advance for using Fahrenheit. Alright, let's make a little chart of that. So the x-axis will represent the time, the y-axis will be the temperature, and I plotted a dot right here to say that at 1 o'clock it was 50 degrees. Alright, let's say we're interested in what the average temperature is between 1 and 3 p.m. So at 1 o'clock it was 50 degrees, but let's take the temperature again at 2 o'clock. So maybe at 2 o'clock it shoots up to 60 degrees. So I'm just going to look back at the graph we had before, but this time I'm going to add on another point for at 2 o'clock it was 60 degrees. And let's do one last temperature at 3 o'clock, and maybe at 3 o'clock it's actually 100 degrees. So I know it's a little unrealistic for it to actually be an outside temperature, but that much variance, but that's okay. So let's see what our graph looks like now. So here's what we had before, but now we've got this third point up here saying at 3 o'clock it was 100 degrees. So if we were to compute the average temperature based on just these 3 points of data, what we would do is we'd add up the three numbers, 50 plus 60 plus 100, and then divide by 3, because there's 3 different numbers. We'd say, okay, the average temperature between 1 and 3 is 70 degrees. But is the average temperature between 1 and 3 really 70 degrees? Because we only measured every hour. There's nothing that says that, oh, for that entire hour it stayed 50 degrees, then suddenly jumped up to 60 degrees, and then it was 100 degrees. There could have been other temperatures in between. I mean, for all we know, maybe it was only 50 degrees at 1 o'clock, and then thereafter it was like 0 degrees for a while. It was freezing, and then it just at 60. So we could be more accurate by taking more measurements. So let's actually look at this sort of in-between spot. So how about we measure at 1:30. So maybe at 1:30 it's 40 degrees. So going back to our graph, we're going to add a little point in between here. So let me go ahead and do that. So kind of dip down a little bit. So there's 1:30. Let's also maybe measure in half-hour increments. So instead of every hour, we'll go every half hour. So now let's look at 2:30. And maybe at 2:30, well, let's be really crazy here, it was 130 degrees Fahrenheit. So for some reason, in between 2 and 3, it was just way, way up here. So let's add that point on. Way up there. Alright, well now, see before we thought the average was 70 degrees, but now we can get a more accurate picture of the average. So instead of 50 plus 60 plus 100 over 3, let's throw in the 40 and also throw in the 130. But now instead of dividing by 3, we have to divide by 5, and now the answer is actually 76. But can we actually say, alright, that's the average between 1 and 3? Well, it's more accurate than measuring every hour, because we measured every half hour, but we could actually just measure every 10 minutes. Or how about every minute? Or every single millisecond, right? So in the end, you sort of have like this infinite number of values, and like how do you divide by infinity? Seems kind of crazy. So how do we actually accomplish this? Alright, so the key is to turn this into a continuous function. Well, it's not like we're turning a continuous function. It was already a continuous function. We just had little discrete measurements of it. But here's sort of a blow-up picture of our graph so far. But we don't know exactly what's going on in between the dots. So I'm just going to draw something crazy on there like that. So, alright, what we want to do is sort of figure out what's the average value that this function takes on. So how are we going to do this? So we'll just call this f of x. And we know that when we're dealing with finite values, this symbol means sigma to add them up. So it's saying add up all the temperatures, those are the y values, and divide by the number of numbers. But in this case, see before we had it with 3 numbers and then 5 numbers. Well, what if we measured every single second, however many seconds are in between the 2 hours that we're dealing with? So what we really want to do is take the limit as n goes to infinity. So the x sub I, by the way, that's like these tick marks on the x-axis, right? So as n goes to infinity, you get more and more x1, x2, x3, x4, and so forth. Alright, so we've got to sum up all the f of x's, and then divide by the number of ones that we took, then take this limit as n goes to infinity. Well, this kind of looks a little familiar. it's reminiscent of our Riemann sums, right? It's reminiscent of the definition of integral. So let's kind of rewrite this in a somewhat leading way. So rather than dividing by n, I'm going to write it as times 1 over n. And I'm going to multiply top and bottom by the same thing. So rather than 1, I'm going to put a b minus a up here at the top, and then a 1 over b minus a over here. Because now this looks an awful lot like our definition of integral. So I just have this 1 over b minus a in front, so I'm going to pull that out in front. And rather than writing b minus a over n, that is our definition of delta x. So now, this part over here, the limit as n goes to infinity of the sum of f of xi times delta x, this is our definition of integral. So I can just rewrite this and say, all right, we have now motivated a good definition for the average value of a function over an interval. It's just 1 over b minus a, in this case our b was 3 and our a was 1, of the integral from a to b of whatever your temperature function is. So that's the definition of the average value of a function. All right, this makes a good segue into sort of a new form of the mean value theorem. But first, let's remind ourselves how the old MVT went. So MVT was the mean value theorem for derivatives. I never really said for derivatives before, but this time I want to be specific that we're talking about it for derivatives. So what did that say? Well, essentially what it says is that there's some time in which the instantaneous rate of change is equal to the average rate of change. Now, if we want to say that in terms of symbology, it says that for some c in between a and b, f prime of c is equal to f of b minus f of a over b minus a. Or to think about what it looks like graphically, it's saying there's a tangent line which is parallel to the secant line. In fact, let me just sort of draw the picture there. So here is your crazy graph of f of x. We're going to, all of this, by the way, is on some interval. I didn't actually specify in all of this, but really what I'm saying, there's some point on an interval in which the instantaneous rate of change is equal to the average rate of change over that interval. In this case, the interval is a to b. So here I'm saying there's a tangent line parallel to the secant line from the endpoints of that interval. So if the interval is a to b, then we just put that secant line on there, and then somewhere there's a tangent line parallel to that. I know my drawing didn't make it look very parallel, but in essence, remember the slope of the tangent line, that's the derivative, and f of b minus f of a over b minus a, that's just the slope of the secant line. All right, well, all of that is just a very quick recap of MVT for derivatives. Well, let's look at the new MVT. So let me go ahead and everything we just did, I'm going to shrink off to the corner so we can refer to it. But let's look at the new MVT. This time it's for integrals. So what does it say? Well, in essence what it says is that at some time a function achieves its average. Well, let's write that in symbols now. So it says there's some point, f of c, where c is in between a and b, which is equal to its average. And we just justified a little while ago that this is the formula for the average of the function over the interval a and b. So it's saying there's some point in that interval where you actually hit your average. So that doesn't happen in finite cases, right? Like in that first case when we had like 50 degrees, 60 degrees, and 100 degrees, well, the average was 70, but none of those numbers were 70. But if we have a continuous function, I should say there's an assumption of continuity for all of this. Again, I didn't write that down, but there's an assumption that everything here is continuous and differentiable in the case of mean value theorem for derivatives. So, I lost my train of thought here. What was I saying? Oh, right. So it doesn't work in the finite case. If you just have three numbers, none of those three numbers have to be their average. But if you've got this infinite collection of values, it turns so if we have that infinite number of different temperatures in between 1 p.m. and 3 p.m., if the average between 1 and 3 p.m. turns out to be 72 degrees, that means at some point in between 1 p.m. and 3 p.m., it had to be exactly 72 degrees. So, well, what does it mean graphically? Well, graphically it's saying that there's a rectangle with an area the same as the curve, same as the end of the curve on that interval. Again, always talking about an interval. So let's just draw the picture. So here is the area under the curve between A and B. It's saying somewhere over this interval we can just draw a flat line. Looks like it might be about right there. So again, I'm kind of picking a C, looking at f of C, drawing that line. So this rectangle has the same area in that rectangle as the actual area under the curve. You can think about it as a cutoff line right here, where the part that you're over the line, if this was like dirt or something, I could then cut off this dirt and fill in the holes where it was too low. And it would match exactly the area. So, now by the way, it makes sense that graphically this is the same as this formula, because if you just multiply this b minus a over, what it says is b minus a times f of c, which is the area of this rectangle, would be equal to the integral. Alright, but how would we actually prove this result? Well, it turns out the proof is actually very short because it follows directly from the mean value theorem from derivatives. We can use the mean value theorem for derivatives, which we already proved months ago, to prove this new version, the mean value theorem for integrals. So all we need to do is choose a suitable capital F here. So the capital F I'm going to use is the function, the area function from a to x of lowercase f of x dx. Well, what happens if I put this formula in for capital F into the mean value theorem for derivatives? Well, the first thing we have to do is take the derivative of capital F, right? So, well, the derivative of capital F is just the derivative of this integral. Well, the fundamental theorem of calculus says that's just f of c, right? Because the derivative of the integral just gives you right there the function value. So, and now I'm just continuing what it says right here. So, capital F of b, well, capital F of b would be the integral from a to b of f of x dx, which I wrote right there. Then we have to minus capital F of a. Well, capital F of a would just be the integral from a to a of f of x dx. And I have to divide all that by b minus a. Well, this simplifies very nicely because what can we say about the integral from a to a? Well, it's one of the properties of integrals. It's zero. It just goes away. So what are we left with? We're left with the integral from a to b of f of x dx divided by b minus a. Hey, that's our definition of the average value of a function. So this says, using MVT for derivatives, there must be a c in between a and b where f of c, the function value, is equal to the average value of the function. And that's what we wanted to prove.